Moving actual real-world money is basically a distributed systems nightmare. If you're a backend developer, you already know the terror of trying to bridge the chaotic physical world with a pristine, perfectly balanced digital ledger. So today, in this explainer, we're diving into exactly how Stripe Issuing uses rigorous documentation, ironclad state machines, and highly structured event flows to keep your fintech app from just completely bleeding money. Picture this. A customer swipes their card offline, high up in the sky. There's literally no internet. That means there's no glowing authorization request hitting your server, no real-time webhook firing off, and no immediate balance check. Nothing. But their account still absolutely needs to be charged when that plane eventually lands. How exactly does a database handle a sudden, massive reality check like that without totally corrupting the ledger? Well, to understand how we engineer systems to survive those kinds of edge cases, we're going to walk through the agenda today. We'll start with the fintech nightmare. Dissect the anatomy of an authorization, dive into the chaos of captures and refunds, survive the dispute battlefield, and wrap up with ledger order. Okay, Section 1, the fintech nightmare. This is where physical world anomalies just completely shatter our standard API expectations. See, our digital systems have to account for some wildly unpredictable human behaviors. Take a standard gas station. The network automatically slaps a $100 hold on the card because, well, it has no idea how much fuel you're actually going to pump. That hold often shrinks down to a $50 capture. But restaurants, they do the exact opposite. They authorize the flat $50 bill up front, but later they'll overcapture to, say, $60 because of a handwritten tip. Your state machine has to seamlessly handle these shrinking and expanding amounts without messing up the user's available balance. Moving to Section 2, Anatomy of an Authorization. Let's look at how we actually bring some order to all this chaos. To prevent these anomalies from just destroying our database, Stripe relies on a meticulously documented, event-driven architecture. Every single card swipe kicks off a really strict chronological flow. Right at 0 milliseconds, Stripe automatically checks the balance and spending controls. By 50 milliseconds, it fires off an issuing authorization request event straight to your server. Your system runs its custom logic, sends a response back, and finally, right at the 2000 millisecond mark, Stripe finalizes the decision and fires a created webhook, locking in that state. But here is the catch. As a backend engineer, you are on a ticking clock. Your system has exactly 2 seconds to respond to that real-time webhook with an approve or a decline. If your servers are running slow, or if you hit a random database lock and miss that tiny window, Stripe is just going to default to your fallback settings so the user isn't standing there stranded at the cash register. In distributed systems, latency isn't just a minor inconvenience, it's an actual failure mode. And believe me, the absolute last thing you want is a 3 a.m. PagerDuty alert because a slow SQL query is causing mass declines at the point of sale. Now check out this specific JSON flag, is amount controllable equals true. I love this because it brilliantly illustrates how weird physical edge cases are explicitly baked right into the API payload. If your webhook sees this flag on a gas station authorization, your code immediately knows, hey, I don't actually have to accept this default $100 hold. It can respond by approving a partial amount instead, which protects your user's balance from being completely locked up by an automated fuel pump. And regardless of the final amount, the core state transitions here are totally ironclad. You approve it, which deducts funds and places a hold. You decline it, which instantly closes the authorization with zero impact to the balance. Or you just let it expire. If a merchant forgets to actually capture the funds, Stripe just automatically releases the hold after a set time frame. Your ledger effectively heals itself, which is huge because it saves you from having to write a bunch of custom reconciliation scripts just to hunt down orphaned holds. All right, Section 3, Captures and Refund Chaos. Holding money is one thing, but moving the actual money is where things get truly wild. See, capturing funds isn't just flipping a Boolean switch in a database. It requires a highly orchestrated atomic ledger update. When an authorization transitions into a capture, 4 distinct things have to happen simultaneously. First, the original authorization status is set to closed. Next, an authorization release transaction is created to free up that temporary hold. Then, a brand new capture transaction object is minted. And finally, the actual purchase amount is permanently deducted from your balance. It is this beautiful multi-step dance of debits and credits that maintains perfect idempotency. But what happens when a merchant's logic just completely fails and they accidentally trigger a webhook twice, issuing a duplicate refund? You definitely can't just run a SQL delete command on a financial database. Instead, you have to execute what's called a refund reversal. It is literally a transaction where the type is set to refund, but it has a negative amount field.
So, a negative $10 refund acts as a mathematical correction. It balances the books without breaking your immutable audit log. Honestly, it's such an elegant solution to a terrifying bug.
Which brings us right back to our offline airplane scenario, the force capture. Because that terminal was completely offline at 30,000 feet, it couldn't ask your server for permission. So when the plane lands, the network just forces the transaction through anyway. It creates a capture object where the authorization field is just entirely null. Your automated reconciliation jobs absolutely must be robust enough to handle these unlinked, out-of-the-blue ledger deductions gracefully without throwing a massive exception or paging you in the middle of the night.
This brings us to Section 4, the dispute battlefield. This is all about defending your ledger against fraud and failure.
The API documentation here really acts as a strict legal runbook. You can't just fire off an HTTP request saying, hey, my user wants their money back. You have to provide precise combinations of tokenized evidence. Disputing a duplicate charge, you have to supply the original transaction token. Claiming some merchandise wasn't received, you need the exact expected delivery date timestamp. And notice the special rule. If the transaction was authenticated using 3D Secure, the network liability shifts, meaning you often just cannot dispute it at all. And the stakes here are incredibly high. Card networks enforce a very strict 110-day expiration window for fraud disputes. If your system is automatically managing thousands of these disputes, you have exactly 110 days to gather the evidence, format the JSON payload, and submit it. If you miss that window by even a second, the status irreversibly transitions to expired, and that money is permanently gone. It's a hard deadline enforced at the network level. There is zero room for buggy retry logic here.
This all builds into this massive asynchronous lifecycle that can span across months. You start at day 0 with an unsubmitted draft, which lets you safely append evidence. Once you submit it, the payload is locked. And then you just wait. It could be 45 days, it could be 90 days. Eventually, an issuing dispute closed webhook will fire, transitioning the state to 1, which magically reinstates your balance, or lost. It's essentially the ultimate long-polling state machine. Finally, Section 5, Ledger Order. Let's see how all of this integrates into a cohesive, perfectly testable financial architecture.
Now, testing distributed systems in production with real money is obviously disastrous. That's why Stripe provides these dedicated API test helpers. You can programmatically simulate total chaos right inside an isolated sandbox. You can force an automated fuel dispenser to lock up $100, trigger unexpected incremental hotel charges, inject terrifying unlinked force captures, or even submit disputes using the exact string winning evidence. This lets you safely test how your system handles a sudden influx of reinstated funds, letting you battle test the absolute worst-case scenarios before they ever happen in prod. Ultimately, whether it's a messy, unlinked refund, a delayed 30-day hotel capture, or one dispute, the end goal is total reconciliation. On platforms using Stripe Treasury, these issuing transactions map beautifully via a simple treasury field directly to a received debit or received credit resource. It completely transforms unpredictable physical world's chaos into an immutable, perfectly trackable digital ledger. No orphaned rows, no mysterious disappearing funds. This whole flow brilliantly illustrates how robust documentation and strict API contracts aren't just nice-to-haves, they are the literal foundation of a reliable data system. They are the only thing standing between a functional fintech product and absolute financial chaos. You really have to design for the edge cases, the partial captures, the delayed webhooks, the unlinked refunds, because in the real world, the edge cases are the normal cases. So, as you go off to architect your next system or write your next webhook handler, I want to leave you with this question. If an offline terminal suddenly forced a massive unlinked ledger update into your database without a shred of warning right now, would your system survive the reality check? Think about it. Thanks for joining me on this explainer, and keep building resilient systems.